Well, good afternoon. My name is Chris Bark, and I want to welcome you to the William W. Hay Railroad Engineering Seminar. And before I introduce our speaker, we have our usual housekeeping items. First of all, if you have a cell phone, please turn it off or turn it on to vibrate so we don't disturb the speaker. If we have a fire alarm, we should exit from these doors on either side of the room, and in each case, just a few steps further, there are stairs down to the ground level where we can exit the building. I'd ask you to use the buddy system, so whoever's sitting next to you, please try to keep track of each other so that make sure everybody's out of the building. It's another beautiful day in central Illinois, so we're not expecting severe weather, but if we were to have severe weather, instead of going outside, obviously we would go out, again, either that door and behind this wall, or out that door and over into the old section of Newmark Lab, descend all the way to the basement, which is a very safe sanctuary. If you didn't swipe your ID card earlier, please be sure to sign the attendance sheet, including your name and affiliation. And if you did not receive a direct email announcement of this seminar, but would like to in the future, please legibly include your email address and we'll add you to the list. I'll ask the speaker if we can't get a microphone to the people asking questions in the audience, if you could please repeat the questions for the benefit of those of us who have joined us via the internet. So, the William W. Hay Railroad Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us, we thank AAR, BNSF, CN, Hanson Professional Services, and the National University Rail Center of Excellence for their ongoing support of RailTech. It is greatly appreciated by those of us here on campus as well as those participating via the internet. I also want to welcome the almost 200 people who have registered for this seminar. They hail from 13 countries on 6 different continents. We're still waiting for Antarctica. And the list of attendees includes freight and passenger railroads, transit organizations, federal and state DOTs, engineering firms, universities, research organizations, technology developers and suppliers, and others. We're very pleased that you could join us for our seminar today. Those of you who wish to receive PDHs for your participation, please see the instructions in the email that was sent to you or on our website. So, unlike many other rail systems in the world, especially in Europe, mainline railway electrification has not been adopted by U.S. Class I railroads due to various economic, technical, and institutional barriers. However, evolving technology and the emerging demands of decarbonization offer new context for evaluating the economics of freight railway electrification. This seminar reviews traditional obstacles to freight rail electrification and uses a new model developed. It was developed by you and your team, yes, developed by Tyler and his team to demonstrate how these new technologies and strategic operation and implementation approaches can improve the economics of traditional and intermittent electrification on a case study freight corridor. Regarding our speaker today, I'm going to use a cliche. He needs no introduction on this campus. Tyler Dick was my first MS student beginning his studies here in 1999, following completion of his Bachelor of Science in Civil Engineering at the University of Manitoba. He's now an assistant professor in the Department of Civil, Architectural, and Environmental Engineering at the University of Texas at Austin, where he leads the Texas Railway Analysis and Innovation Node, and I'll let you guys figure out the acronym. Prior to joining UT Austin in 2022, Dr. Dick spent 10 years as a researcher and lecturer here in RailTech, including completion of his PhD in 2019. From 2001 until 2012, he was a railway design engineer with HDR Engineering, where he attained the title of Professional Associate. At UT Austin, Dr. Dick and his team are conducting research on railway operations, railway capacity, and alternative transportation energy topics. Dr. Dick is a licensed professional engineer in the state of Texas, is chair of ARIMA Committee 16 on Economics of Railway Engineering and Operations, chair of the TRB Joint Subcommittee on Railway Capacity and Performance, chair of the ASCE Rail Transportation Committee, and serves on the board of the International Association of Railway Operations Research. Please join me in welcoming Dr. Tyler Dick, who will present today's Hay seminar entitled Modeling the Economics of Modern Options for Mainline Freight Railway Electrification.
All right, well, thank you, Chris, and good afternoon, everybody. It's great to be back here in Central Illinois, great to be back on campus. A lot of great memories in this room and even before this room existed. The last time I gave a Hay seminar was, I believe it was 16 and a half years ago, okay, which means I'm really old now, right? This part of that bridge didn't exist, this part of the building didn't exist. We were over in the Granger Library, and I think we needed 4 pizzas in total to serve the entire group, right? We have a few more today, but it's always good to be back here on campus. I'm excited to go to the basketball game tonight, and so hook 'em horns and go Illini, right? So today I'm here to present some of our research that we worked on for the Federal Railroad Administration, so modeling the economics of modern options for mainline freight railway electrification. I do want to acknowledge my co-authors. So Rydell Walthall, he's my very talented doctoral student down at UT who did a bulk of the economic modeling work, and also Michael Iden and Jim Blaze that were my collaborators on this project from a private industry perspective. Okay, so let's start out this seminar by going back in time and looking at yesterday's vision of the railroad of tomorrow. Back to 1969, the cover of Railway Age, the Muskingum Electric Railroad, okay? Test tube for tomorrow, the vision for what the future railroad could look like. And I can see Chris is getting up because I didn't turn the lights off. There we go. All right, so the future vision for tomorrow's railroad, right? So what did this railroad of tomorrow have, right? It was unit trains. They were automated, autonomous operation, no crews on these trains, and they were electrified. Okay, so that's the subject of today's seminar. So how do we do this in terms of the vision for the future? Right, well, we've got unit trains are pretty ubiquitous on freight rail network in North America, so we got that checked off. Automation, we're still trying to get there, right? Unless you go to Australia, here in North America, we pretty much have 2-person crews, that's the mandate. And what about the last one, electrification, right? Well, not yet, obviously, but has the time come for that in the future, okay? Is that something we might expect? And that's kind of the goal of this research, is to understand what are the prospects for mainline freight railroad electrification going into the future. So we had this project with the Federal Railroad Administration to look at and better understand what were the primary technical, economic, and institutional barriers to freight rail electrification in the past, and are there different innovative solutions that have been established since 1969 and when freight railroad electrification was looked at that could change and improve the benefits and reduce the cost and risk equation, make it more attractive as an alternative for decarbonization in the future, and to accommodate that, develop this new risk-based framework to evaluate the cost and benefits of freight railway electrification, especially considering that it's not just a question of private railroad investment to minimize energy consumption, but also looking at how does it affect the impact of decarbonization and climate goals in the future. So to that, we developed something called the current model for the economic analysis of freight railroad electrification. I'll introduce that later in the seminar. So for the first part of this project, we went back and reviewed previous studies of looking at freight railroad electrification. So we looked at 53 different studies. The plot here in the top right kind of shows the distribution of where those studies fell over time. So a lot of studies from back in the 1960s and 1970s that were done by the railroads themselves. Also some of the FRA study that was extensively done on electrification in the 1970s and early 1980s. And also a lot of utilities and manufacturers were involved in this as well. So you'll see some examples of that as I go through the talk. So that's sort of the distribution of the studies we looked at. And kind of the short story of this, I'll go into a little more detail, but the common themes that we kept emerging is that the primary barriers are economic and institutional. Okay, there was nothing technically preventing freight railroad electrification from taking place, but most of those barriers related on the technical side were related to uncertainty of how this would translate to the North American freight environment. There was a lot of experience from Europe, from elsewhere around the world, but not a lot of historical experience to draw upon to understand exactly how this might work in a North American freight operating context. Okay. The other thing that we found from reviewing the literature is that many of these proposals really entered advanced stages of engineering and design. You know, there's complete schematics for entire subdivisions of Western United States that are designed out and how the catenary would look at, where all the substations would be, but less developed was exactly how this would be financed. Okay, how did the economics of this actually work? So that was something that we found as we looked through the literature. So one example of some of these different studies, I'll use this, is the Southern Pacific Railroad. They were actually one of the leaders in studying freight railroad electrification back in the late 1960s and early 1970s. Okay, so I'll step through some of the studies that we had access to. We had great cooperation from the people that have the Southern Pacific Railroad Historical Archives out in California. They sent us a giant box full of documents, memos, inter-office communication between different management people at Southern Pacific Railroad back in the 60s and 70s when they were really discussing the potential for freight railroad electrification. So let's step through a few of these studies. So back in 1966, they started off, the first mention of it was electrifying from Portland, Oregon down to Klamath Falls, Oregon, okay? And this was great. The local utilities said, hey, we've got incredible low-cost power for you. This is going to save you a bunch of money. And the railroad said, oh, that's fantastic. Let's look at this. Let's study this. And the utility's like, oh, well, we only really have this cheap power at night, right? Can you run all your trains at night when we have excess electricity and not use it during the day? And the railroad was like, well, that doesn't really work with us, right? So that quickly didn't really go anywhere. The next study was looking at Donner Pass, heading from Roseville, California up to Sparks, Nevada. They thought this would be a great route, very energy intense, demanding, going uphill. But when they looked at how can we get enough electricity out to this remote location, the cost of the transmission was going to be prohibitive. Okay, so that very quickly fizzled out on that side. The next year, they were approached by one of the local utilities, Southern California Edison, approached the Southern Pacific Railroad and said, hey, we're having a lot of problems finding right-of-way for our transmission lines to access the Los Angeles area in Southern California. It'd be great if we could build our transmission lines along your rail lines going into the area. Could we strike up some sort of deal? And that sort of instigated a lot of relationships between the railroad and the utility, and how can we use our right-of-way to be able to use it for transmission access to a very developing, crowded type region. That deal kind of advanced. There's a lot of discussion to it, but the problem became there was sort of an uncertainty in terms of the long-term pricing structure of what energy costs would be. So the railroad was looking at, well, we need to make this long-term investment, but we need to know what the cost of electricity is going to be 10, 15, 20 years into the future. And the utilities weren't really, the utility involved wasn't really ready to commit to that sort of a long-term pricing deal. So the economics of that study didn't work. The most advanced and most well-studied route was this route, the long-distance route, the Sunset route between just outside Los Angeles, so Colton, California, where they had their major terminal, going to El Paso, Texas. Okay, so the Sunset route. And they had a partnership with 5 different utilities to develop electrification on this really extensive, heavily trafficked corridor. They looked at that for a number of years, roughly a 5-year period from 1969 to 1974, got to really advanced stages of engineering and design. But as they dug into it, they found there was a lot of uncertainty in what some of the exact costs would be, particularly related to what they would have to do to upgrade the signal system. So one of the things I gained a new appreciation of when I did this study was when you electrify a corridor, your existing DC track circuits are incompatible with an AC electrification because you return that alternating current through the rails. So you have to completely replace the signal system when you electrify a freight rail corridor in North America. There was also a lot of uncertainty into how all of the clearance constraints along this corridor would be resolved. So everywhere where you have a highway overpass or a tunnel or a through-truss bridge, you potentially have to make some modification to that civil infrastructure to accommodate the clearances for the overhead catenary system. So there was a lot of uncertainty on those fronts into how that was going to factor into the costs. There was a lot of uncertainty into the financing type arrangements. And ultimately, they wanted to push it to the board several times to vote on this. And then in 1974, the traffic on Southern Pacific Railroad just cratered. A huge freight recession. And from that, the railroad really never recovered financially. So all the talk of electrification suddenly became something that went for the history books. Okay, so what is the problem here related to why was all this uncertainty in the costs a problem for moving freight railroad electrification forward? Okay, a lot of people just say, well, it's expensive. Okay, well, lots of things railroads do are expensive. Okay, double tracking the Transcon route on BNSF was expensive. Double tracking the Sunset route by Union Pacific Railroad was expensive, right? But those costs are justified and they're taken on by the railroad. So why is the expensive cost of electrification in particularly problematic from an investment standpoint, from an economic standpoint for the railroads? So let's take a look at a typical pattern of capital investment for an electrification type project. So I'm plotting here over time costs and benefits for electrification on a corridor. Okay, so we start off the project for 5, 6, 7 years, however long it takes for us to electrify a long distance corridor. we have nothing but costs for building the OCS, which are quite substantial upfront, okay? So we have years of these costs when we're not getting any benefits. And then finally, we complete the OCS and we purchase a bunch of new electric locomotives, right? A big, huge lump investment in that final year. And then finally, after that, right, we have no initial benefits. We're still operating with diesel freight on these corridors. And then suddenly, right, we fire up the OCS, we electrify everything, and then we get energy cost and saving benefits, okay? And also comes along with that is a reduced maintenance cost for electric locomotives compared to diesel electric locomotives. And over time, that you hope that those energy cost savings and those locomotive maintenance cost savings outweigh all of that initial upfront investment, okay? So if you look out far enough in time, all of those savings will eventually offset all of those costs, and you have some sort of positive benefit cost ratio for the project, okay? So that's fine in terms of a long-term perspective, but let's look at what people sort of in the finance department really care about, right? What is the cash flow impact of this project on the railroad, right? So we have, in this case, 6 years of nothing but cash going out, paying for stuff, right? So we dig ourselves a giant hole, okay? We sent a lot of money outside the railroad, and it's going to take years and years and years for those tiny little annual benefits to offset that incredible upfront investment, okay? So it takes many years, in the case decades, in the case of that Southern Pacific project going from El Paso to Southern California, it was going to take them 16 years before they actually got to a positive cash flow position, okay, before they recovered all the outgoing cash. And they impacted it was going to take 8 years for their stock price to recover if they made that investment. So from an investment standpoint and sort of a cash flow perspective, it's a huge problem to have such a giant initial capital investment because the return doesn't come for many, many years into the future, okay? What's the other problem with this, right? You're relying on benefits derived from the difference between the cost of electricity and the cost of diesel fuel 10, 20, 30, 40 years into the future, okay? How well do we know the cost of gas, let alone next week, okay, let alone 30, 40 years into the future, right? So the problem is a lot of these energy cost savings are a crystal ball prediction of the future and a huge amount of uncertainty what those are going to be, right? So there's a lot of cost and uncertainty related to your energy cost, and all of these benefits, right, are a function of how much traffic you have on the corridor, right? If your traffic goes down, you run fewer trains, right? You're consuming less energy, and overall, you've got less savings to offset that initial investment you made in OCS, right? So we have a lot of uncertainty. So what could happen to our cash flow, right? If we don't have a big enough differential energy prices, we don't have enough traffic, we may never, ever recover this investment, okay? So it could be an economic loser in perpetuity if we make the bad assumptions on traffic and the savings of energy. Okay, so this creates tremendous financial risk. Okay, so it's not that it's expensive, it's just an incredibly risky investment that only pays off in the incredibly long term in terms of freight rail electrification. Okay, so that's the economic puzzle that we're trying to put together, is how can we change this equation to make this more attractive as an investment? So you might be wondering, well, what about my title slide on my presentation, right? I had that beautiful picture of the electrification in British Columbia, right? So how did that happen, right? So in 1983, the British Columbia Railway, okay, established a new 81-mile electrified route, okay? So how did that decision get made given these horrible economics for freight rail electrification that I just outlined, right? Well, there's some different things about this. This was a project, it was a brand new project that was built to access brand new coal mines that were being developed to mine coal, ship it out on the railroad through Pacific ports, and send it to Japan for steel-making purposes, okay? And part of that project was there was a guaranteed 15-year shipping contract. The railroad knew for 15 years they were going to get exactly this much coal shipped at exactly this much revenue, so they knew all of the benefits that were going into this project were guaranteed, okay? So that took one chunk of the risk out of it, right? The other thing was the cost of this electrification was incremental because on this route they had 2 very long tunnels that they were going to have to ventilate, okay, to ventilate the exhaust fumes out of the tunnels so the crews weren't exposed to them. The cost of doing that was essentially just slightly less than the cost of electrifying the corridor, For that ventilation system, they had to bring in power. They had to have substations to power the giant fans for that ventilation system. So at some point they said, hey, it's just cheaper to just electrify this corridor than it is to build this ventilation system for these tunnels, okay? And there were also the idea that these electric locomotives, okay, were higher horsepower compared to the equivalent diesel locomotives available at the time, so they could save on the actual acquisition costs of these locomotives. Even though the electric locomotives were more expensive because there was very few of them being constructed, it was a net savings in that end as well, okay? And the final, okay, and this is a point to consider going to the rest of the discussion, is that they received a grant from both the federal government and the provincial government to support this project, okay, because they were going to be doing some renewable energy related to clean air type, conservation type things, very early type of environmental grants to help support this project as well. Okay, so that took some of the risk out of it as well. All right, so this is why this project worked. So how do we reduce the financial risk in other types of situations? Okay, so when we go back to the historical studies, the railroads and the Federal Railroad Administration both looked at different alternative financing arrangements to sort of reduce and spread this risk. Okay, so they wanted to figure out how can we reduce this initial capital investment burden on the railroads and spread this risk amongst other parties that are potentially going to benefit. Okay, so we guarantee the money financed for these projects. So several of these things, they came up with this idea, could we create a separate entity to finance, construct, operate the OCS? Okay, basically assume that risk of ownership so it didn't fall on the freight railroads themselves. So there's some different partnerships, Southern Pacific and those 5 utilities, they came up with this idea that they were going to create this separate subsidiary company called Catenary Associates, okay, that would build all that OCS infrastructure between El Paso and Southern California. A similar type scheme was proposed, the Railway Electrification Management Corporation by the Southern, the Louisville and Nashville Railroad, and the Tennessee Valley Authority on the routes south of Cincinnati, okay, going down through Tennessee. And the FRA, when they did their sort of national electrification study, this last landmark study that was done looking at the entire network back in 1983 by the Transportation Systems Center, which eventually became Volpe, okay, they looked at electrifying, 10,000 miles of the network, and they were going to develop a federal FRA railroad joint venture, okay, where the federal government was actually going to help subsidize the construction of the OCS. So what does the railroads do? Basically, after all the OCS was constructed by this third party or this FRA joint venture, the railroads would just have to purchase and maintain electric locomotives, and they would basically pay a use charge per kilowatt hour of electricity that they consume to move the trains. Okay, it's kind of like you had a toll authority build the tollway, and they were just paying a toll in terms of however much electricity they actually used to move the trains. And eventually, over time, either the joint venture or these private corporations would recoup their initial investment in the overhead catenary system, and then it could potentially be transferred through the railroads to actually be owned and operated by them after that initial investment was recovered. Okay, so that's some interesting different ways of financing railroad electrification. So we can think about this as how this goes into the future, right? These partnerships are essential. Okay, so this is part of what we had to consider in creating our new framework for modeling future approaches to freight railroad electrification. Okay, so is this a really crazy idea, railroads actually paying for electricity, okay, instead of paying for locomotives, right? So we fast forward a few years, okay, the Burlington Northern Railroad, one of the predecessors of BNSF, they actually used this same concept in the late 1980s and early 1990s. They called it power by the hour, okay? And they basically said, we're tired of paying for inefficient locomotives that break down all the time. We pay for this asset and then it doesn't really give us a really good return on investment. So they said, we don't want to pay for the locomotive. We just want to pay for the electricity that it generates. Okay, so they had leasing firms that actually purchased and financed that capital investment. They were responsible for basically maintaining those locomotives. And Burlington Northern just purchased the electricity that they actually generated that went to the traction motors. Okay, there's literally an electric meter in the locomotive that they used to pay for. Okay, so there was 2 companies, Oakway and LMX, that leased these out. You recognize them. These are pictures of these locomotives from the late 80s or early 1990s. But what it did is it motivated local manufacturers to improve the reliability, okay, the utilization, the uptime of the locomotives, and also increase the locomotive efficiency. Okay, so it's not too crazy of an idea to think about railroads just paying for electricity, because that's really, really what they need to move the trains instead of investing in this capital asset. All right, so how do we address these economic barriers? Okay, we talked about there's this problem, right, of too much initial investment, too much uncertainty into future benefits, right? How do we change this economic equation, right? So what could we do if we have projects that look like this? What can we do, right? Well, there's a couple things we might look at. First of all, the obvious thing is decrease the costs, okay? How can we decrease the cost of freight rail electrification? And how can we decrease that project timeline, shift those costs further to the present day, okay? Because that's going to help us from an economic perspective. What else can we do? Let's figure out a way to create some initial benefits, okay? The earlier we can get those benefits in the project, the better that's going to impact our cash flow if we can get some returns from this investment, okay? What else can we do, right? We can increase the scope and scale of those later benefits, okay? So we get greater benefits over the longer term. And what's the final thing we can do? What can we do to get rid of this crystal ball, right? What can we do to replace that with something that's more certain, okay? Something we can more precisely measure in the long term, right? How can we have more certainty over the results of this investment? So the challenge for our project was to look at what things are out there, what technologies, what implementation strategies, what ways of approaching freight railroad electrification give us these types of effects. Okay, what can we do to move benefits forward? What can we do to create initial benefits? What can we do to increase the overall scope and scale of the benefits for freight railroad electrification? So that's kind of the framework that we're working in when we looked at these different technologies. All right, so to address some of these barriers, we looked at a variety of different technologies and strategies as part of our project, okay? The first, we're looking at other methods out there to streamline catenary construction. Can we reduce the cost of it? Can we do it faster? Okay, there's a bunch of different things we could look at. Electrical efficiency improvements, different voltages, okay, auto transformers, changing the substations, changing the actual design of the catenary, optimizing it, ways that were not possible using computer-aided design compared to back to the 1970s when you were drafting everything out by hand. It's a lot easier to optimize the catenary design. New construction techniques, for example, these catenary construction trains that they have over in Europe, okay, make this a much faster type of process. You can build a lot more miles of catenary in a construction season than you could before. And are there different alternatives to the OCS, okay? Unfortunately, looking at things like third rail or induction, just are not technologies that are not ready for prime time in a freight railroad type environment, so they're quickly discarded. So overall, some of those methods to streamline the catenary construction, there's some different things that you could do out there, but they're not really going to be a dramatic game changer, okay? They can slightly change the cost, but they're not going to revolutionize the economics from a freight railroad type perspective. We also looked at different locomotive technologies. I'll talk about those a little bit more in subsequent slides. We also looked at something called intermittent electrification or discontinuous electrification, or DISCO-CAT is the cool acronym that people like to put out there. I'll talk about that in a couple slides. And then also we looked at different implementation strategies. Okay, so thinking back to some of those partnerships, Catenary Associates, this FRA joint venture, how can we leverage some of those different partnerships to make freight railroad electrification more attractive? Okay, if you think back to the 1960s and 70s, things like public-private partnerships, D-bombs, 3Ps, right? Those things didn't really exist back then, right? But now they're very, very common ways of delivering massive infrastructure projects that require a lot of capital investment up front. Okay, so we'll talk about some of these other partnerships and need for to monetize different benefits here in a couple subsequent slides. So, locomotive perspective. One of the most promising aspects from the locomotive perspective was the idea of, can we develop dual mode locomotives or locomotives that operate on different types of power sources, okay? So the problem, part of the problem that we have with that economics is, right, we have no initial benefits from OCS, right? We have to install catenary over thousands of miles before we electrify an entire corridor, and then we have traditional electric locomotives operating on that corridor, all right? So the idea we have is, can we utilize our existing AC traction diesel electric locomotives to actually utilize power drawn from the overhead catenary? Okay, so Mike Iden, who's on our team, he has this scheme that he's developed. He says, if you have a diesel electric locomotive, if we go into the back, we can feed in power into that locomotive, and use those same traction motors on the diesel electric locomotive to feed in power drawn from the OCS by something called an electric power tender. Okay, so we couple this electric tender behind the locomotive. If there's no overhead catenary, it runs as a straight diesel. When we get to a section with overhead catenary, we raise our pantograph, draw power off the overhead, feed that across the coupler into our locomotive, and it operates as if it was an electric locomotive. Okay, and this allows us to, as we construct OCS along the corridor, mile by mile, segment by segment, as we complete it and energize it, we can draw power off of that OCS, eliminate diesel section by section by section. So if you go back to that previous plot I had, after that first year, after you get that OCS done, the next year you've gotten energized. You're getting benefits off of that section. Okay, instead of having to wait 6, 7, 8 years until you get enough of a network completed that you start electrified operations. Okay. The other thing we can do is we can add battery capability into that locomotive. Okay, so can it actually continue to operate in electric mode where we don't have OCS? That'll help us connect branch lines, terminals, sidings, okay, where it's very expensive to electrify into our network. It does add some complexity. There are questions related to maintenance and training, but really the benefits are potentially going to outweigh some of those detractors from this approach. So it's going to reduce our capital costs compared to straight new electrics because they're using our existing diesel electric locomotive platform. And it's going to allow us to move those benefits sooner. Okay, so we can get our electrification, get those benefits running sooner. We can also potentially motor through those gaps in the OCS. So we don't have electrified territory, we either fire up the diesel or use a battery to move through those different segments. Okay, and the other key thing is avoiding locomotive changes along the route. Okay, that is an operational impact and operational disruption, which is another challenge against freight railroad electrification. If you can't do the whole network, stopping to change locomotives at different places is an interruption. Those delays create costs that add to the costs and the disbenefits of the electrification type scheme. So that's on the locomotive side. So that locomotive technology leads to this concept of intermittent electrification. As I've said before, the infrastructure cost, okay, we typically dismiss freight railroad electrification all the time because we have this high cost, right? One of the cost sources is going through for additional electrification everywhere we have a highway overpass. Okay, most highway overpasses don't have additional clearance to put the overhead wires above the clearance that we use already for double stack containers. Okay, if they were built with additional clearance, when we went to double stacks in the 1980s, that additional clearance was taken up to allow us to operate those heavy rail cars. So we have to make this major investment to raise all these highway overpasses or address the clearance issues, lowering the track, different ways of approaching it. Okay, so we have that perspective on electrification. We can also look at, well, what if we don't build OCS and just go with batteries, right? We know that has limited range. We can only put so much battery storage capacity on a locomotive. Even if we use battery tenders, we're just not going to get very far along our corridor. So the idea is, can we use these two technologies in tandem, right? The strengths of both to come up with a way to reduce the amount of overhead catenary system we need to construct. That's going to allow us with a more economical type project, right? So we have different schemes of this. We really have a sort of spectrum that goes between traditional full OCS and battery alone. We have something called battery-assisted discontinuous electrification. So we're typically using OCS, electric locomotive with a small battery, and everywhere we get to a bridge or a tunnel or something that would be, where we have clearance issues, we create a gap in the OCS. We don't put overhead wires next to those structures. We rely on our battery to motor through that gap. We can also think about, well, do we really need OCS everywhere, or can we operate mainly on batteries? And then when we get to segments where our batteries are running low, we construct a segment of overhead catenary system and use that to charge the battery on the fly. Okay, so how can we have these two technologies work together to give us improved benefits? Right, so we need to balance both the extent of OCS and the required last mile battery size. So it's a bit of an optimization to figure out, given the topography and the nature of the corridor, where do we need OCS, how big does the battery need to be, and what's going to give us the most economical solution for a different corridor. So that's where some of the economic modeling and optimization comes in on these projects. All right, The other thing we talked about is increasing the scope of benefits. So when you go back to the historical studies, they're always talking about, well, our main benefit is we're avoiding the cost of diesel fuel and instead having a lower cost for electricity. So we'll get net energy savings, okay? Our current framework, right, we have additional benefits from eliminating the emissions from diesel locomotives, because we know that that has social impacts in terms of health impacts to local populations adjacent to the rail lines, and also global impacts in terms of climate change from those emissions. And the US Department of Transportation and the EPA assign cost values to those emissions, right? So the table here is if you operated a typical mainline 4,400 horsepower locomotive at full throttle for 1 hour, depending on how old that locomotive is, so which of these locomotive emissions tiers it falls into, the costs there are the valuations placed on all the different pollutants and all the different carbon emissions that come out of that locomotive, right? So if you take a tier 1 locomotive, you operate at full throttle for an hour, that's just under $2,000 of impact that you're having, okay? So in theory, if you electrify, get rid of those emissions, right, you are saving, in sort of a grand sense, $2,000. The challenge, of course, is that is not real money in the sense of the railroad can't take that $2,000 and put it into an investment into catenary, right? We need some mechanism that captures this public global benefit to put into and finance into the actual infrastructure, okay? So we need some sort of mechanisms to value capture and transfer this, this value to the railroads. The other question you're probably going to have when you get this, see this is, okay, well, this is what's coming out of the locomotive, but what's coming out of the electricity, right? Not all of our electricity is clean, right? Not all of it's coming from renewable type of sources, right? So the plot here we're showing on the map, the darker the color is in these different regions of our electrical grid, the more carbon intense the electricity is, right? So here in the Midwest, here in central Illinois, a lot of our power is coming from coal, right? So a lot of that power is not exactly the cleanest in terms of carbon emissions, right? So offsetting, having electrification in the Midwest, when the electricity is just coming from a coal plant, right, not going to give you as much benefits as elsewhere in the country where maybe it's coming from hydroelectricity, wind, and solar, like places out in the western United States where you have a lot more renewable electricity. So this is something we had to factor into our model is where's the electricity come from in different parts of the country. The final sort of area that has changed since the 1970s is the motivation of the utilities, okay? The electrical transmission grid, there's huge demand to connect some of those renewable areas or areas of the country with a lot of renewable energy, okay? A lot of wind and solar to where a lot of demand is taking place, okay? Places in the Midwest and the southern United States where there's a huge demand and expansion in terms of population, developing data centers, charging for other electric vehicles. And the studies that have been done by the energy DOE is there's just billions and billions and billions of dollars in investment required to expand the transmission grid. Okay, so that prevents an opportunity for the railroads. Okay, the railroad right-of-way going all the way back to Southern California Edison, going to Southern Pacific back in the 1960s, the railroad right-of-way is a great right-of-way for utilities to use for transmission. Okay, so there's a potential opportunity here for a railroad to offer its right-of-way to a utility and say, hey, locate your transmission line along this right-of-way, and you can deal with just us, the railroad, as the only landowner, instead of having to go and negotiate with hundreds of individual landowners along this entire route. Okay, that's a much more efficient way to design, permit, obtain the right-of-way for a transmission line. So there's some examples of this. CPKC is working with utilities to create this Sioux Green HVDC link. So it's a high voltage direct current line that's actually buried underground alongside the rail line going from Mason City, Iowa into Chicago, okay? So it's a 250-mile line going to connect some of the wind power in Iowa into the Midwest and bring renewable electricity where it's needed here in the Chicago area. So some of the benefits here could be, could you structure this deal to provide the utility with access to the railroad right-of-way in such a way that you've got revenue from the lease, okay? So that's additional benefit that could go to electrification. You could say, hey, you know, we'll let you locate it right away if you give us free connections to the grids to support electrification. And you could structure a long-term discount on your long-term cost of electricity, okay, by hosting the utility to relocate or co-locate in your railroad right away, So this is an area of another opportunity that we were foresee in the future that wasn't really a factor 50 years ago in the previous electrification studies. So in summary, what has changed from back then to now, right? Then it was the cost of diesel versus electricity. Now it's what's the best way for freight railroads to decarbonize, okay? The utilities back in the 1960s, they had tons of inexpensive power coming from coal and nuclear plants. Now it's like, we don't have enough electricity, but we need a lot of right-of-way for transmission, okay? Railroads were reacting to the oil crisis and fossil fuel security. Now there's a push for diversity of energy sources. Can we hedge against the cost of oil by getting energy from different sources? From an environmental perspective, back then it was local smog and noise pollution was the motivation for electrification. Right now it's the public health and climate change documented effects of diesel that we're trying to avoid. And from a technologies perspective, back then it was all or nothing with OCS, and now we've got potential for batteries, other technologies, dual mode locomotives to change the way that we electrify a corridor. So within that context, we've developed a model that can look at different approaches for freight road electrification, okay, within this new decision context, right? We call this model the current model, so something called the costs, uncertainty, and risks of rail electrification with new technologies, or current, okay? I can't take credit for that acronym, okay? My doctoral student came up with that one, right? It was great. All right, so what this is, a framework, okay, can allow different electrification deployment strategies, do the economic analysis. It includes a train performance calculator that my student developed in Python, okay, to estimate the energy consumed by a train over a given corridor. And it goes through an Excel spreadsheet that does a full benefit cost analysis, okay? And then on top of that, to capture in all of this uncertainty and risk, we have a Monte Carlo simulation that runs within Excel using this Argo plugin, which is something that we just learned about. It's really cool. We'll talk about in the next slide. So some of the inputs required for this model, we need to know about the route, we need to know about the traffic, and we need to know all this unit costs and other parameters that go into the model. And it outputs all the different costs, okay, the capital, maintenance, energy costs. It looks at the emissions, and it looks at the different net present value, the rate of return, and also, after doing this Monte Carlo simulation, what's the distribution of this rate of return? So what's the estimate of the risk and the possible outcomes from these different projects given all the uncertainties involved? So as I said, we use a Monte Carlo simulation running within Excel. So there's this plugin called Argo. So it's a free plugin for Excel. It was developed by Boozell and Hamilton. Really, really cool. You can actually go through and put it into your Excel spreadsheet and run a Monte Carlo simulation in your Excel sheet, which is really cool for lots of other research topics, not just railroad electrification. So we go through, we can specify for all these different cost parameters, like what's the cost of electrification, a substation, what's the future cost of energy. We can specify a high, low, and expected, and what that distribution should be, right? Is it normal? Is it a triangular distribution? And it'll go through and iterate through, do thousands of simulations within a few minutes, and spit out a distribution like this of what our rates of return look like for different alternatives. Okay, so something that's really, really useful. All right, so to wrap up here, I'm going to talk about a case study that we did of different approaches for freight rail electrification. So we looked at a double-track mainline corridor with fairly dense traffic, so something that would be fairly ideal and attractive from a traffic perspective to electrify. So we chose just over 1,000 kilometers, or just over 600-mile corridor from Kansas City, Kansas to Clovis, New Mexico on the BNSF double-track Transcon main line. Okay, so it's a long route which would traditionally require many, many years of OCS implementation, so probably 6 or 7 years to construct the OCS in a traditional manner. And it has a strong potential value as a utility corridor because it connects regions of the United States that have a lot of wind and solar to areas in the Midwest that need that power and electricity. Okay, so over here on the right, we're plotting, this is the elevation profile along that route, okay, going from Kansas City on the left up to the high desert in New Mexico on the right. And from a traffic perspective, we just chose some representative traffic since we didn't do this in cooperation with BNSF. We were just using their corridor data. So we had roughly 60 trains a day composed of intermodal, bulk unit trains, and manifest trains on this corridor. And typically we had 3 or 4 locomotives per train from a traffic perspective. So we looked at 4 different electrification scenarios: the full traditional electrification with overhead catenary system, The option was short gaps with the last mile battery, where we avoid the infrastructure costs for raising bridges and increasing the clearances. A progressive electrification with dual mode, where we can fire up the catenary and run a dual mode as we build each year by year on the corridor. And an intermittent electrification, where we had larger gaps to charge those battery locomotives as they made it across the corridor. And our model looked at 4 different perspectives. We looked at a pure private railroad investment, a private railroad investment with utility sharing, a private investment where we were able to capture and monetize all those public health benefits and climate change benefits, and then looking at this from a pure public project perspective. So going into some of the results, so this is for looking at the traditional sort of approach for conventional overhead catenary system. This is looking at the actual cost of the infrastructure over time. So it would take us, in this case, just under 5 years to actually construct that OCS. And the cost of it is roughly $2 billion to construct OCS over that corridor. And you'll notice here a large portion of the cost, just under half of it, is replacing the existing signal and communication system. Okay, so it's not the overhead catenary system, it's the incompatibility with the signal system that's a huge cost driver for the freight road electrification. The other big item here is the public works cost, right? So $150 million is raising bridges, improving clearances on different segments. So that says, hey, maybe this option where we can use a last mile battery to motor through these gaps, right, to avoid those costs, right, that's going to take a fairly big chunk out of that, okay? So the next slide here shows us the results when we look at the actual cash flow or the benefits and costs over time of our conventional OCS. Okay, there's a lot going on in this plot, but we've got our initial investment, we buy our locomotives, and then we get all these benefits coming in. Okay? And what we find is we get a really long-term good benefit cost ratio of this project, but it still requires that large initial investment, okay, a large amount of risk shared by the railroad up front. Okay, so it may not make it attractive from a pure public-private investment. So down here I've gotten this table here plotting from different perspectives, so each row in the table is a different perspective, okay, from the private perspective with right-of-way sharing, with the subsidy for the health and climate benefits, and then from a pure public perspective, we're looking first at the net present value, then the internal rate of return, and then the benefit cost ratio over here, and we've got different discount rates. Okay, so if you look at this from a public perspective, you're likely to use a 3 or 7% discount rate. A railroad is going to use like an 18% discount rate because they want to get that investment made back really, really quickly. That's sort of their standard, right? So what we find out is when we get to the sort of private railroad investment with that 18% discount rate, we get a huge negative net present value, right? Something that is not very attractive from a railroad perspective, okay? Even though we have a 7% rate of return, that's not really going to get a lot of railroads interested in this project, okay? However, when we start going and adding in, right, the utility sharing helps a bit. If we actually have some mechanism, okay, to either make this an entirely public project or to monetize some of those benefits, we start getting into a rate of return in the 20% range, which is going to start getting some attention from the railroads, okay? But that's only if you have some mechanism to capture that value and transfer it into dollars, which can go into infrastructure. So the utility partnerships improve the economics, but still this public support might be necessary to bring about the private investment required to can move forward with these projects. All right, so what about the other alternatives? Okay, OCS with the short gaps, right? We've got electric locomotive with a last mile battery. We motor through. We assume that we make breaks everywhere. We have a clearance constraint, avoid all those public works costs, take out that $150 million cost, right? The numbers start improving a little bit, okay? Didn't really move a whole lot, but we're starting inching towards something that's going to be more attractive. What about progressive electrification? Okay, we use these dual locomotives. We've got electric power tender, okay? We go through, we assume that we have the same gaps in the OCS as above, but we can start using operations as we build each section after each year on the corridor. Okay, we can fire things up and start running trains earlier in the project. We get these initial benefits, and we start getting into something where we're starting to improve further. Okay, we're getting close to a 10% rate of return when we start factoring in utility sharing. Okay, so getting into something that's starting to get attractive, but still not quite there yet. But from a public perspective, we're getting close to a 30% rate of return. Okay, so that's something that projects that should seriously be looked at if you can bring about that sort of project and that sort of public partnership to finance a project in that manner. So what about our intermittent electrification case? Okay, the biggest question we had was, where do we have to put all of our battery operations? How much OCS do we have? How much batteries do we need? Okay, so we had to do a lot of assumptions on where do we put the OCS? How much can we charge off of the OCS on different parts of the corridor? So this was an initial scenario we looked at where we had 24 megawatts of power to draw off the OCS. 30% of the route was going to be covered with OCS, and it was unsustainable. Okay, so as a train traversed the route, by the time it got to the other end, the batteries were down at a low state of charge. That train's going to have to spend all day in the terminal recharging, and that's just going to kill your locomotive utilization and kill the economics of the project. Okay, so what we want to do is be able to run this across the corridor where we get to either end at a high state of charge, so we don't have to spend time in the terminal charging up all those batteries and kill our locomotive utilization, increase the cost of the locomotive fleet. So we went through and did a bunch of iterations, looking at different combinations of coverage and different combinations of power on the catenary, and finally came up with the case here at the top that 30 megawatts of charging at 40% coverage could give us a sustainable operations. Okay, trains could cover the route, okay, and not have to get to the terminal and be recharged. When we looked at that type of implementation, we were able to greatly reduce the cost of our overhead catenary system. Okay, so instead of having a $2 billion investment in OCS, we reduced it down to $530 million. Okay, so roughly 75% of our capital investment in the OCS itself went away by adopting this scheme. Of course, the trade-off, of course, is we have to have more batteries on the locomotives, which increases our locomotive fleet cost. So, what's the grand scheme from this, or what would have this do with the economics? Okay, because we had to add that extra cost of the batteries in, we don't get a huge change in our sort of private perspective, but our public perspective greatly increases. Okay, so now we're into roughly 30+% rate of return from a public perspective, and including some sort of a value capture from the health and climate benefits of electrification. So this is, again, something that really, if you can have that type of partnership, okay, is potentially going to move these projects forward. But from a private perspective, it's still not something that's really going to be very, very attractive for the railroads to do on their own. So the other issue, right, we looked at what is the uncertainty in this. So the left is plotting the distribution of rate of returns from a private perspective, and the right is from a public perspective. There's still a lot of uncertainty in all of these costs and benefits that go into these estimates. Okay, we don't really know everything about what electric locomotive maintenance would be, what these dual mode locomotive maintenance would be compared to traditional diesels, right? So we get this wide range of uncertainty. Depending on how these different estimates of all these different parameters fall, we could have very high or very low rates of return, even in some cases, approaching very single digits from a private perspective that are not going to be very attractive at all. So there's a lot of uncertainty still out there. So this slide just goes through and compares them all side by side. Okay, so you can see here, as we sort of increase or come up with these different technologies and apply them sequentially, going to using batteries to motor through the gaps, progressive electrification with dual mode, and then finally progressive electrification with dual mode with the gaps with intermittent, right? We improve our rate of return from both a private and a public perspective for each of those sort of advanced ways for approaching electrification. So what's the big takeaway? Okay, the barriers to traditional freight railroad electrification are both economic and institutional. There are some key methods that we can use to improve the economics of freight railroad electrification. Okay, we can use dual mode locomotives or progressive or intermittent electrification schemes to reduce the amount of OCS we need to construct. Partnerships with utilities for transmission, okay, in exchange for lease payments or favorable electrical rates are going to be key to this in the future. But ultimately, we need some sort of public partnership to monetize these climate and health benefits by infrastructure investment is going to be the key to making this work going into the future. So even with these technologies and partnerships, when we did this Monte Carlo simulation, we found all of this huge distribution and all these uncertainties, right? So future research can be used to provide greater certainty and reduce the risk related to these different investments. So that's where this current model comes in. Be able to better understand what parameters are driving the risk and what's important, and really these utility partnerships can allow us to spread the inherent risk related to future energy prices. But ultimately, one of the things that we really need is a lot of future research and demonstration projects related to some of these alternative technologies. How exactly would intermittent electrification work? How efficient are some of these dual mode locomotive approaches going to be? And one of the key ones here is understanding what's the actual impact of OCS on signal systems that are equipped with positive train control. Okay, so that's something that wasn't really understood and very well covered in the literature. That's a real expense that could vary quite well into the future, a major source of uncertainty and risk. Okay, so the bottom line is it's not that it's expensive. It's expensive, but it creates great benefits over the long term. And that creates a lot of uncertainty and risk. Okay, so it's a risk-based equation is what we're taking away today. With that, I want to thank you for your attention and want to acknowledge the sponsorship of the Federal Railroad Administration. There's the disclaimer there that we have to put into it. But thank you for your attention today. It's a great opportunity to come back and speak to you here on campus.
Well, great seminar, Tyler. Do we have any questions here? I've got several. So one scenario I don't think you considered, but maybe it is with a different name, is what about if the utility companies built the electric infrastructure and the railroads bought the locomotives and sort of sold electricity like you were talking about earlier in your talk?
Yeah, that's a good question. We did not approach that exact arrangement like we talked about that they're envisioning back in the 1970s with the partnerships with the utilities and that sort of a build, transfer, build, maintain, transfer type partnership. My student is actually working on this week. He's been building a model from looking at this from the utility perspective, trying to understand what sort of a lease agreement would make sense for transmission in terms of how their costs and how their benefits would change from the utility perspective. So we went with more of the co-location as opposed to the utility actually constructing all of the OCS and everything. So, but when you sort of look at this from a pure public perspective, you actually capture some of that arrangement, because that just says, okay, globally from a public perspective, we don't care exactly where the investment is coming, whether it's coming from the utility or the railroad, it has to be made, and this is what the public benefits would be. So that is somewhat captured in that perspective on the bottom line of some of those slides.
Okay, but it would also occur to me that there's from the railroad perspective, if all they were doing was buying locomotives and buying electricity, how would that change?
Right. Yes, that's one thing we don't have. We don't have that split out from what the railroad perspective would be if all of the investment got offloaded to a third party. So that could be something that we could tease out of the numbers that we have within the model.
Yeah, I think they'd be interested in those numbers. Right. I'll ask another question. So I just heard this, I guess, last week at the conference, this notion that the cost to the train control system is such a major factor. And I guess I'm surprised at that in the context of PTC. Was that applying to conventional wayside signaling, or was it applying to PTC?
So the costs that we had, last slide we have it broken down. Well, here's a good example. So that cost is the conventional signal system, based on what that estimates would be. But part of it is understanding, are there additional impacts to the positive train control system? Or is that cost going to be higher or lower on a corridor equipped with positive train control? So one of the concerns could be that the OCS creates some additional interference with the positive train control type system, or having the OCS over top of your GPS antennas on your locomotives requires some sort of mitigation strategy. The flip side potentially is that if positive train control were installed as a vital type system instead of an overlay system, then you could eliminate a lot of the wayside signal infrastructure, right? You'd still need broken rail protection in some manner, but that could reduce the signal system impact of having the return current going through the rails. So it's not so much that it's PTC, but understanding does positive train control have an incremental cost on top of just the traditional impact on signal systems? Is something that we weren't really able to identify from the past literature just because of the lack of experience in that area.
Yeah, so actually I'm glad you stopped on this slide because I was surprised at the substantial reduction in the signaling and communication cost with this option. I don't fully understand
Well,
that.
part of this is if you're only building OCS along 40% of your corridor, then the sections that are not having OCS, you could not, you basically avoid having to upgrade the signal system on that corridor. That's that assumption of how is the signal department going to like having the signal system change on OCS versus the gaps, right? They're probably going to want to say, well, we got to replace the whole thing, right? So that's one assumption of sort of this economic shakes out.
Okay. The last point I'll make is, do you know that there are commuter rail authorities operating on the Northeast Corridor using, what's the conventional PTs?
The access?
They're not using access.
Okay.
Is it ERTMS?
Yeah.
ERTMS, I guess. Anyway, the one that the rest of the country is using. So I would think there's some information out there. I believe both Mark, for sure, I'm fairly sure Mark is doing this, and there may be others. So that could be worth exploring.
Right. The other challenge of the Northeast Corridor is depending on which segment of the Northeast Corridor are they operating at the same frequency and voltage that you'd be looking at for, this is envisioning looking at 50 kV, 60 hertz, freight rail electrification versus some of the segments in the Northeast Corridor that are different combinations of frequency and voltage.
All right, so we have a question in the room, then I'll go to the internet.
So if technology like this were to be implemented with, like, say, discontinuous catenary, is that more likely to be AC or DC current, and why?
Yeah, so most of the modern systems are using AC type current because you get AC electrification. You can basically have fewer losses along your corridor, and also it simplifies the cost because you can use your grid power to power the electrification. It makes your substation simpler. You don't have to have the conversion process at the substation if you use the commercial voltage, commercial frequency, and obviously being AC coming off of the commercial type system.
All right, hang on, let me get one from the internet and then we'll go to you. When is the research paper behind this presentation coming on? I think that's the FRA report.
Yeah, so the FRA report goes into the FRA publication process, and people chuckling in the room is we never quite know exactly when it's coming out the other end. I've got my student, he's been working on several papers derived from this research that we're hoping to get submitted and published in journals very, very soon, but I unfortunately can't tell you when the final report will come out of this.
All right, I'll do a couple of questions from the internet because we have a lot. The e-tender idea is very cool. How much additional power is needed to drag the e-tender, though? Yeah,
so that's actually factored into our train performance is when we, obviously going to vary depending on the corridor, but we do factor in the additional train energy requirements by adding in either the electric power tender or the battery tender or the additional last mile battery on the locomotive. So that's factored into the energy consumption. We can't split it out exactly. We could tease it out of the numbers, but we are accounting for the additional train weight penalty on that for additional of the tender or additional battery tenders.
Here's a question from a former colleague of yours. The Pennsylvania Railroad began using electrified freight back in the 1930s. Did you look into that, and were there any lessons learned from them?
Yeah, so in the final report, so I just went through the Southern Pacific Railroad case study. In the final report, we do go through the Conrail experience on them then deciding to discontinue their electrified freight operations and not expand the existing legacy electrification from the Pennsylvania Railroad. We also look at Union Pacific Railroad And we also take a deeper dive into the LNN, Southern, and TVA type agreement as well. So I won't specifically address it in this presentation, but in the report we do look a lot at some of the other railroads that were involved in this and some of the studies that were done.
I guess I'll ask a follow-on to that question. As you know, Conrail inherited all that electrified territory and opted to eventually retire their electric locomotives and run diesel under the wires. Did you guys look into that, what the reason for that was?
Yeah, I mean, there's a lot of reasons related to renewal of the electric locomotive fleet and then just the divergence of energy prices in the early 1980s. So Conrail stopped electrified freight operations in 1981, I believe, that time frame, and you look at where the costs of the two energy sources were going, and suddenly the economic motivation behind that went away from a perspective from an energy source and also from just needing to renew the locomotive fleet as well. But that's covered in the report.
Hi there. In your presentation, you've talked about lots of great alternatives to the conventional electrification. I was just wondering, is there any? These are all theoretical. I was wondering if there's any you looked at. Is there anywhere in the United States or beyond that have practically tried to implement any of these ideas yet?
Yeah, no, that's a really good question. So obviously here in the United States, we don't have experience with this from a mainline freight perspective, but there are a number of electrifications done internationally that use the discontinuous approach. So in Scotland and in the UK, there are some operations where they went with a discontinuous approach to reduce the costs. So it's from that sort of perspective, some of the logistics and practicalities of it have been worked out, but obviously not within the exact North American freight context.
How do you think that changes and improvements in batteries and charging can impact your model?
Yeah, so that's a great question, right? So thinking how many years ago, 10 years ago, we did a study for California Air Resources Board, and we wanted to look at battery technology. And at that time, if we wanted to power a train over any sort of distance, a quarter of the train was going to wind up being, locomotive or battery tenders full of batteries. And then since then, battery energy density has tripled, right, in that time frame. So anytime we get any sort of improvement in battery chemistry or energy density, it's going to change these economics more in favor of we can get further and further with the batteries. It's not just the battery storage, but as you said, the battery charging as well. So that's a whole piece, and I'll talk about that in the graduate seminar this afternoon and some of our battery modeling. But the amount of time required to charge the batteries is going to improve our intermittent case, okay, because we need less and less OCS to recharge the battery. And then if you try and go with a pure battery option, whether that's for mainline or in yards and terminals, the big obstacle now is you can get 14 megawatt hours of storage on a really, really big locomotive, but you can only charge it at half a megawatt per hour, right? So 28 hours of that thing sitting charging, right? That's not going to get a railroad excited, right, when that locomotive winds up sitting around for an entire day charging, okay? So chargers and battery storage are also a big piece of this, especially particularly on the intermittent electrification scenarios.
Okay, I have a follow-up on the IETMS, the PTC question under catenary. One of our alumni who's working on PTC said that Mark runs IETMS under Pennsy OCS, Caltrain is running IETMS under Modern OCS, and Denver RTD also runs IETMS under Modern OCS, so there may be some resources to pursue.
Excellent.
Back to the internet. Partnerships between railroad and utility companies was mentioned with respect to right-of-way sharing. Could trains be a noticeable liability to utility companies' transmission lines? They're thinking about a derailment, knocking out a transmission line above or below ground and cutting power to a major city.
Yeah. I mean, it's any sort of risk. I mean, if you look at the utilities, what they're doing, they're co-locating in highway right-of-way as well. So if you drive up from here up towards Minneapolis on Interstate 94, all through Wisconsin and Minnesota, they're building transmission lines right alongside the interstate. Obviously, having a train derail and potentially impact your transmission is always a risk. I think you just have to factor that into your pylon design for your transmission towers and what that looks like. The same way that when you have a grade separation, you've got columns for supporting that grade separation next to the tracks. You do protection on that, crash wall protection, right? So the same type of thing. Is it an incremental cost on the cost of transmission? Potentially, right? So that's something that need to be weighed against the economic benefits of being able to streamline the construction process in a railroad corridor.
Okay, next question. Did you include any income from regenerative braking, i.e. rather than dissipating electricity produced from dynamic braking, instead feed it back into the grid? This may only be practically economical in specific mountainous regions.
Yeah, so when we factored in the electrical consumption cost of all these different alternatives, we were factoring in regeneration to offset the power draw, right? That was the simplest way to do that, is if you had regeneration, that would be a credit towards your electricity cost. So we are factoring that in.
Okay. Is there an optimal distance to electrify that would maximize benefits and minimize costs?
Yeah, I'm hoping that my grad student's dissertation is going to tell us, what some of these optimal type schemes are going to look like. So, the FRA project was to develop the framework. We still want to run more case studies. And one of my goals for my student in his dissertation is to wrap this into an optimization framework to figure out, for a given corridor, how much OCS do we need, or what sort of the optimum, project would look like from this perspective.
Okay. On slide 14, and I don't think you need to go there, the valuation of NOx, PM, et cetera, what's the source of these values?
So those are from the benefit cost guidance published by the US DOT and the EPA, used for evaluating all sorts of transportation type projects. And they give it on sort of grams of the different pollutants. And we basically looked at the EPA emission standards for the different locomotive tiers and did the multiplications to translate those into dollars based upon the horsepower hours.
Okay. What about railway companies allowing utility companies to install small modular nuclear power stations on their land?
That's a good question. So that's something that we didn't look at. I think it was way back when this call came out. That was something that was mentioned within the overall BAA project scope, but I know that's something that Department of Energy and ARPA-E are really interested in, the micronuclear reactors and what that could do for power supply out in rural areas. But that's something we specifically did not look at within the scope of this project.
Next question. AC operated railways in Europe are successfully using DC track circuits. It's not ideal, but it works.
Okay, well, we'll investigate that.
It's my understanding that current crossing predictors, grade crossing predictors, are incompatible with AC electrification. Did your economic analysis include the cost to replace these crossing components?
That was factored into the signal and communication type costs, was also the grade crossing warning devices. And there's a couple other questions here in the room as well.
All right, we'll go back to the room.
So David, go ahead. I can shout it out.
I had two questions, but I'll just do one. What's the primary cost in upgrading the signal system? Is that to deal with return current in the track circuits or something else, and why?
Yeah, no, it's the replacing all the track circuits, going through and dealing with that.
What makes them incompatible? Does the current mess with the electronics or what?
Yeah, so you're having to put the return, basically putting in, return of 50 kilovolt AC power through your track circuits, which could be DC, right, which obviously is incompatible, or there's some sort of a different frequency, a different voltage of AC that, is incompatible with that. So having to convert it over to something that, isn't going to, you're not going to fry all your track circuits by pumping through that current through your return.
Okay. So my question is, where do you think the electrification, if railroads go with this, where will it, I guess, begin? Will it begin more in cities where utility companies need to get access to the grid better and like there's more concern about like NOx and particulate matter, or will it begin in the rural areas where it's like cheaper and more, I guess, economical?
Yeah, definitely. It's a good question. You know, it's going to begin where some railroad is willing to go out there and take the chance, right? That's ultimately where it's going to be. And the cost of this definitely in rural areas in terms of you know, permitting, in terms of potential interferences for clearances and things is more likely going to be in a rural type area. You know, that's where it's going to have to be, I think, from a standpoint. But it's challenging because you need to have a long enough segment, okay, that makes sense. So one of the reasons for the Clovis to Kansas City case study is those are two areas where naturally you're doing refueling of locomotives on the main line. So it's a potential location where if you do have to swap over to dual mode locomotives or electric locomotives or electrics with last mile batteries, it's sort of a natural place where you're stopping, doing an inspection of the train anyway. So there's less impact from an operational perspective than if you just choose a random segment somewhere, right, to install this.
Okay, here's a kind of a combination question from the same individual. How are costs and benefits impacted by number of tracks and train tonnage and track profile? How do they affect the cost benefit?
Yeah, I mean, the model can answer all those questions, right? You can put in different track profiles. You can very quickly change the number of trains. Obviously, the traffic level, right? The more traffic you have on the corridor, the more you're going to distribute that initial capital investment, right, over more trains that are sort of saving more energy and more returns. But you do have additional costs for locomotives. The topography, you know, is obviously going to affect the energy demand. So it's kind of like you gain these sort of economies of scale. The more energy demand you have, the higher traffic you have, which is why the railroads have always looked at, traditionally everyone that's studied this has always tried to identify the highest tonnage, highest traffic corridors are the ones that are going to be most attractive for that capital investment.
Here's another question from an alumnus who's trying to build a high-speed rail line. What was the source of your estimated OCS installation cost?
Yeah, I mean, we went through and looked at all the 53 previous studies that were done. And we looked at some of the more recent ones and then tried to adjust for inflation and different increases in material and construction costs to give a best estimate of what the cost would be.
Okay, some more good questions here. First, complimenting your presentation. Are there economies to having the entire network electric? In other words, is OCS less attractive if there's a combination of electric, hydrogen, LND, and other locomotives?
That's a good question, right? There's efficiencies that are gained if you had everything on one operation because you avoid the potential issue of locomotive exchanges. But at the same time, there's going to be corridors where, you know, the same way that you can't invest, you know, welded rail and concrete ties and a CTC control system and branch lines that don't have the traffic to justify it, right? It goes back to the Wellington laws that we talk about in class, right? And matching the investment to the level of service and the quality of service needed to be provided, right? Electrification is the same way. There's many branch lines, many low-density corridors that are just never going to justify that capital investment. You know, the same way when you look at operations in Europe, there are still many branch lines that are still not electrified. They're running with diesel or hydrogen or battery or some other technology besides traditional OCS.
Another question from an alumnus who says, did all of your scenarios consider AC electrification, or would the economics differ for DC?
Yeah, these were all ACs. We were all looking at 50 kV AC electrification. We didn't really explore the other. We looked a little bit in the report and some of the other alternatives, but we didn't explicitly run those through the model.
Okay. Other costs to consider are inspection and maintenance facilities, employee training costs, and costs of disruptions to train traffic. Amtrak's electrification between New Haven to Boston was about $720 million for 150 miles of double-track corridor. So not a question, but it's coming from somebody who should know.
Yeah, we did include in the model. There are provisions in there for the maintenance facilities that you would require for the new locomotives, and we do have a line item in there for retraining your personnel to the new technology. So again, it's what the cost should be for every different corridor. It's developing the framework, and we've got entries in the model for all those different cost items.
There's still quite a few more questions, but I think we'll wrap it up pretty soon. But what are your thoughts about state/government built and owned OCS? It's related to my other question, but.
I mean, we've got the provision in there to look at this as a public type project. From a practical perspective, it depends on how amenable, the freight railroads are going to be to having some massive amount of infrastructure within their right-of-way that is not completely under their control, right? So when you look back at the agreements, there was provisions. The FRA study that was completed in 1983 had full participation of the railroads when they proposed looking at some sort of a federal railroad partnership for constructing the OCS. Obviously that didn't move forward for a variety of different reasons, but that was something that the railroads that were involved in the study were essentially, to the extent that it made it into a final study, was something that was not immediately cast away, right, as something that was an impossibility. And you look at, the track record over the past 10 to 15 years, railroads have become much more acceptable to having public investment in their infrastructure type projects through going back to the, Recovery Act, reinvestment to Tiger grants, the Chrissy grants, those things, 20, 25 years ago would have been, no, we don't want any of that, federal government type investment. But now it's much more common to have these public-private partnerships that result in freight rail infrastructure. So I don't think it's too ridiculous of an idea to think it could be a possibility. But again, it's what's the amenable? Are the railroads going to be amenable to having a public-owned infrastructure within their right-of-way is the question.
I think we'll just do one more. We can get all these questions to him, right? Yeah. Does the current model consider losses due to disruption in train operations during new catenary construction?
We have a factor in there that you can, I know somewhere in the model there's a little knob you can turn, right, that factors in additional costs, cost increase due to disruption of train operations during construction. I can't remember exactly how we set that for the case studies, but it is a consideration that your costs on a brand new corridor or a corridor where you have low traffic are going to be much easier to construct OCS on a corridor that has high traffic density, which unfortunately is the most attractive corridors to construct this, are the ones where you are going to be most difficult to get the track time to actually build the infrastructure, which is the unfortunate equation behind this.
Okay, well, I'll just conclude with a very high compliment from one of the listeners. Amazing work, standing ovation. So on that note,
Thank you.